Okay, welcome to part 2 of methods for inducing anabolic pathways. Part 1 we talked about metabolic stress. This time we're going to talk about mechanical stress. So which can be induced by increased force as well as increased stretch. So one of the things you want to maximize tension it's going to impact tension is going to be rest period length. So if you look at if you look at 50% of your 1RM, you look at the total repetitions from set 1 to set 2, 3, 4, and 5. When you have 1 minute rest versus 3 minutes rest, you have more total repetitions. If you look at 80% 1RM with 1 minute rest versus 3 minutes rest, you have more total repetitions. So basically what this is indicating is that the longer you rest, the more total tension you're going to have on the muscle per set. So what we think is to maximize metabolic tension, you probably need to rest about 3 to 5 minutes. Now, if we're talking about velocity, as well as the type of contraction, it seems that maximal lengthening or eccentric contractions result in more protein synthesis than shortening contractions. So if you can look, it's real easy to look at B. You see that the lengthening contraction has more protein synthesis than the shortening. If you then go to the right, at the top, middle, and down, we're looking at essentially the proximal, mid, and distal site. And we're looking at protein synthesis. And what you see is that you look at fast training, the dark bars are eccentric, the open bars are concentric. If you look at fast eccentric training, that has a large increase in muscle size in both the proximal, mid, and distal sites of the muscle. If you look at slow training, on the other hand, you get less hypertrophy. And that's sort of the point. The point is that eccentric, fast velocity contractions cause more hypertrophy, and it's likely due to more tension per cross bridge. Because again, what happens is that the slower you go, the more time you have to build up interactions between myosin and actin, or interactions between the cross bridges. The more cross bridges that you have formed, the greater the stress distribution. The less cross bridges you form, the less stress distribution and the greater damage per cross bridge. And that happens with more faster velocity contractions. So again, if we look at contraction type, or speed or velocity, if you look at slow twitch fibers, which is A here, you notice that from pre to post, the fast versus slow both pretty much increased hypertrophy the same in type 1 fibers. So slow contractions stimulate slow twitch hypertrophy. But if you go to type 2A and type 2X fibers, you see that there's a clear advantage for the fast contractile group compared to the slow. So this suggests that slow contractions are not as beneficial as fast for type 2 hypertrophy. Now, why is eccentric contractions ideal? Because if you look at electromyography, concentric and isometric and eccentric contractions, there's less EMG activity in the eccentric. So what this basically means is there's more, again, greater tension per cross bridge with the eccentric than the concentric contractions. We also see here that what we're looking at is action potentials, or essentially the stimulation of fibers. So the soleus is a slow twitch muscle group, and the gastrocs is a fast twitch muscle group. So if you look at shortening contractions only, you get a little bit more amplitude in the slow than fast. But if you go to lengthening contractions only, it looks like the gastrocnemius has greater recruitment than the soleus, which indicates that eccentric contractions preferentially recruit type 2 fibers. I want to emphasize something to you. It's probably the most important part of this lecture. graph A, we're looking essentially here at what happens when you're actually looking at sort of tension, right? So, if you look at tension and force development, if you look at set 1 through set 4, if you have a maximal concentric activity versus a maximal eccentric on A, force development is greater on the maximal eccentric. Okay, if you match maximal concentric for less than maximal eccentric, it's matched for the concentric load. Force development is the same. Okay, so in other words, you can develop more tension with maximal eccentric than concentric. Now this is very, very important because what we're looking at here in graph A is mTOR signaling. Notice that the maximal eccentric stimulates more mTOR stimulation and ultimately greater protein synthesis than the maximal concentric. But when you normalize for the tension, max concentric, submaximal load matched or intensity matched eccentric, both are not stimulating protein synthesis. So basically what we're telling you is that what is special about the eccentric contraction may be related to the fact that you just can generate more tension maximally. Okay, and again, that is very, very important. And again, I can't emphasize that enough. Because what people say is this: oh, the eccentric contraction stimulates the most growth. So then people will mistakenly feel that that means that slowing the eccentric portion to a super slow pace will enhance the response of training, since eccentric training is mainly responsible for tension and induced hypertrophy. However, if you're looking at submaximal concentric exercise and normalize the eccentric portion of that load, then eccentric exercise is no more beneficial than concentric training. So eccentric is likely only more beneficial when you can increase total load eccentrically relative to concentrically. But when you're lifting a normal load, your lifting weight or intensity is based on the concentric activity. Thus, slowing the eccentric is not going to benefit you. And in fact, as we showed previously, a slower eccentric may be less anabolic. So you get double indemnity. We're looking here, changes in muscle size. This study actually controlled for tension, so they had a work match eccentric load to a maximal concentric contraction, and they only did eccentric versus concentric. Muscle fiber size increased more in the maximal concentric. Now, why is that important? Why would it increase more in the concentric when we all know eccentric is the most important? Well, because when you work max control, tension is the same. And metabolic stress is lower eccentrically than concentrically. So you develop more hypertrophy in the metabolic environment with less tension. And that's what we see here. Plasma lactate is higher in the maximal concentric, maximal eccentric, and that is exacerbated when you compare maximal concentric to submaximal eccentric. So what we think is that you're clearly limited on the eccentric portion by how much you can lift in the concentric portion. For this reason, assisted negatives may be beneficial in order to maximize metabolic stress. So basically what you do is you lift normally concentrically, and then your partner pushes down on the bar on the way down. This is an advanced technique, I have to warn you though. Let's talk about fast twitch fiber recruitment. We know that recruitment of type 2 fibers is a prerequisite or very important for skeletal muscle hypertrophy. This is work from Schoenfeld's lab. What you're looking at is the impact of intensity. To the left, we have high intensity training till failure. To the right, we have very low intensity training till failure. And what you'll notice is that the low intensity loads never maximize electromyography even at failure. So they might recruit some high threshold motor units, but they don't recruit the largest ones, and they must be recruiting a lot of slow twitch fibers. Now Campos studied a low group 3 to 5 RM group versus a moderate 9 to 12 RM and a high rep low intensity group 20 to 28 RM, all to failure. So only the heavy group and the intermediate group hypertrophied, and this indicates that intensity does play a role in hypertrophy when volume is equalized. So they controlled for volume in this study. And this is supported by Kumar, what we're looking at is the intensity threshold with young and older individuals. Notice that you don't hit protein synthesis till you hit about 60% of your 1RM. Then it goes a little bit up, and then it plateaus. But again, this is if you look at sort of the 20% 1RM group, they're not going to failure, whereas the heavier groups are going to failure. But based on their work, Kumar proposed an intensity threshold of at least 60% to maximize protein synthesis. So Bird at a Stu Phillips lab came along and had a 90% failure condition versus a 30% failure condition versus a work-matched 30% 1RM trial to the 90% 1RM condition. He had 4 sets and 30 seconds rest between conditions. Notice that the 90% failure condition had a total volume load of 710 kilograms, versus which was matched for the 30 work-matched group, but the 30% fail group had nearly about 80% more volume than the 90% fail group. So even though it was low intensity, it was much higher volume. And here's what we see. If you look at sarcoplasmic, basically, protein synthesis in graph C, notice that the 90% fail condition triggered sort of the most response 4 hours post, but 30% non-failure simulate nothing, and the 30% failure also activated that protein synthesis in that subfraction. Okay, but if you head out, essentially, to myofibrillar protein synthesis, and you look at like 24 hours post, what you're going to see is that only the very high volume group maintained protein synthesis 24 hours post. So this suggests essentially is that early protein synthesis is intensity dependent and later protein synthesis is volume dependent. So volume, irrespective of intensity, seems to be an important variable modulating the hypertrophy response. So this is real interesting. I want you to look at MyoD on B graph, which is to your left, and myogenin, which is your right. So what you're looking at, essentially here, the first group is the 90% failure, second group's work matched, third group is the 30% till failure. Notice that MyoD only increased in 30% till failure, but myogenin increased in both the 90% and 30% to failure groups. They didn't increase in either in the low load group, which suggests that low intensity in the absence of volume is not very anabolic. So this suggests it's now apparent that the extent of myoprotein synthesis after a resistance exercise is not entirely load dependent, but appears to be related to exercise volume. And it's speculated to muscle fiber activation and most likely to the extent of type 2 fiber recruitment. In the current study, MyoD mRNA, which is associated with satellite cell commitment to the myogenic lineage and resultant proliferation of the myoblasts, trended to be greater than the value at rest at 24 hours post-exercise in a 30% fail condition. Whereas mRNA for myogenin mRNA, which mediates terminal differentiation of myoblasts, is intensity and volume dependent. Then if we look at ERK signaling, 4 hours and 24 hours post, we see that ERK signaling is greatest in the high volume group. But this makes sense because ERK does play a role in metabolic adaptations. So again, this is supporting that volume is important. Here you have 1 versus 3 sets, and you're looking at total load is 3 times greater with the 3 sets. Myofibrillar protein synthesis is also greater with 3 sets. So volume plays a role. And we see that sort of with a strength versus hypertrophy workout. So here we have Juha Holmi, Ahatanen, and Walker. And basically what they're looking at is strength, which is blue, 5x10, which is red. And look at P70, ERK signaling, P38, MAPK, are essentially all higher in the hypertrophy than the heavy. So it suggests volume is important. What I want you to look at here is this. So look at essentially the figure to the right. They gave individuals 10% maximal voluntary elbow flexion. You're looking at electromyography. Look at the start of the contraction, very little activity. But as you go from 25%, notice activity increases. 50% of the endurance time, it goes up again. 75%, they're starting to come near failure, it goes up again. In the end of contraction, muscle activity is much higher. So this suggests that fatigue, which is induced by volume or time under tension, plays a role in motor unit recruitment. Even at low intensities, the thought is that as you near fatigue, you do recruit the higher threshold motor units. Maybe not all of them, but you are recruiting some of them. We can see that here. Basically, they're doing force output on an elbow flexor bout, and you look at time from minute 0 to minute 7, you'll notice that muscle activation is going up, indicating greater motor unit recruitment. Then we look here from the beginning of a set, a dynamic and static contraction, from the beginning of a set to the end of the set, you get a 48% increase in muscle fiber recruitment. However, this depends on your training status. So these are recreationally trained people. If you look at 0% up to 60%, motor unit recruitment increases in the vastus lateralis, but by 100% it goes back down, right? And if you look at the first repetition versus the last repetition, you have higher motor unit recruitment in the first than the last. Why is this the case? We think because untrained people, as they experience pain, voluntarily lower their motor output. But this would be different for trained people. This is data from our lab, and what we did was, you're looking at motor unit recruitment and the traditional training. So they did a 10 RM, they trained till their 10 RM max. You look from rep 1 to 10, that's the open group or traditional group. Motor unit recruitment goes up from rep 1 to 10. We had a cluster group where after 5 reps we rested them. We gave them rest in between the sets. So motor unit recruitment goes up from rep 1 to 5, and then it goes down, and then it climbs from rep 6 to 10. The point is that fatigue in highly trained people, you'll increase motor unit recruitment to failure. In untrained people, you may have decreased motor output simply because they can't take the pain. Now, in the Campos study, what you notice is type 1 fibers did not hypertrophy as much as type 2 fibers. So we think type 2 fibers have greater capacity for hypertrophy. We see that here from Fry et al. When you look at type 2 fibers, you get about anywhere from 15 to 30% increases. But if you look at type 1 fibers, the size increases are much less. So what we're looking at is untrained people, and basically they had them do 30% of their 1RM to failure, and then 80%, and then with 1 set, and then you had 80% for 3 sets till failure. Notice that the 80% group and the 30% group both increase muscle size the same. This indicates that you can hypertrophy in an untrained population with the high rep to failure versus the low rep to failure. However, this is one thing Brad Schoenfeld pointed out. If you look at type 1 fibers, this is essentially increase in muscle fiber size. You look at type 1 fibers, the 30% by 3 group increase greater in type 1 fibers than the 80% by 3. Whereas that trend reversed in the type 2. So what this is basically indicating is that this is essentially indicating that the hypertrophy response is going to be very much dependent on the type of contractions you point out. So even though muscle volume was the same, most of the muscle volume responses were coming essentially from type 1 fibers in the high rep condition and type 2 fibers in whatchamacallit. So the muscle group was not, the muscle size gains were not by the same fiber type adaptations. Also, in this study, 8 recreationally resistance trained men did slow contractions with 30% 1 arm till failure and 6-second eccentric versus 6-second concentric. Then they had a work matched control to non-failure. So time under attention, so basically what they did was they did 30% 1 arm till failure with 6-second eccentric versus 6-second concentric. And again, they had a work matched control to non-failure. So basically, one group that just went normal repetition cadence, okay? That's very important to understand. Look at mitochondrial fractional synthetic rate and sarcoplasmic fractional synthetic rate. What you'll notice is that the fast group didn't have much, but the slow group, which is what I'm pointing to, had greater mitochondrial. Now, is this saying that slow contraction is better than fast? No, it's absolutely not. You had 25 seconds time under attention versus 2,000. Again, this is more of a fatigue event. And when you have that much time under attention, you're also going to simulate this sarcoplasmic fractional synthetic rate. So probably if you're looking at the high repetition groups with low weight, they are hypertrophying type 1 fibers, a little bit of type 2, and they're getting more sarcoplasmic and mitochondrial protein synthesis. So the question now is there a minimal intensity that we need to use? Well, Cook, basically in this study, had a high load group, and you're looking at EMG, a low load group, which is 20% to failure, and a low load group plus blood flow restriction. Notice that the black group, which is the high load, the first 5 repetitions and the last 5 repetitions, had more EMG activity than both the low load and the low load plus blood flow restriction. So 20% 1RM is not enough of a threshold when you're going high volume. In this study, they had very intricate design. They had 20% 1RM with moderate pressure, and you're looking at recruitment of type 2 fibers. Then you had 30% 1RM moderate pressure, 40% 1RM moderate pressure, 20% 1RM high pressure. And basically what you're seeing here, and then high intensity, which is all the way to the right. What you're seeing here is that 40% 1RM plus moderate pressure blood flow restriction triggered recruitment of type 2 fibers. So this suggests that if you're going to failure and you're going to use a high repetition range at low weight, you need a minimal intensity of 40% to maximize that response. Anything less won't maximize motor unit recruitment. So let's summarize this. When training, if not going to failure, then intensity becomes the dominant role in simulating hypertrophy. It's maximized at 65 to 85% 1RM in terms of generating increased protein synthesis. Intensity also appears to be an important modulator of short-term initiation of protein synthesis. Higher volumes seem to be an important prerequisite for the initial and long-lasting increase in protein synthesis, as well as the magnitude of protein synthesis. Multiple sets will always result in greater hypertrophy than single sets in trained individuals. Failure leads to greater intensity in motor unit recruitment. Greater number of sets can increase fatigue, as can lower intra-rep and intra-rest periods. Okay, that's very, very important. Low intensity exercise at a threshold of 40% 1RM taken to failure can result in hypertrophy similar to high intensity exercise, at least in untrained people. However, the mechanism of hypertrophy may differ, with low intensity hypertrophying the slow fibers and high intensity hypertrophying the fast fibers. Low intensity failure training may also increase the sarcoplasmic hypertrophy. It's important to use faster velocity contractions, don't slow down the rep, include heavy days with long rest period lengths, and use assisted/forced negative repetition training. Thank you. Oh, one last thing. I want to go back to metabolic stress. Stress the glycolytic system. by training 8 to 15 repetitions. Use short rest period lengths not exceeding 120 seconds. Likely use 90 to 120 seconds for compound and 30 to 60 for isolation. Use supersets, strip sets, and blood flow restriction. Use multiple sets over single sets.